We didn't have any announcements today, so I thought it was a good chance to tell you to, if you're Canadian, register to vote. Otherwise, you'll get old guys like me deciding on your future. And if I was you, I wouldn't like relying on old guys like me deciding on how the country's going to go. So do that. Does anyone have any questions about anything? All right. So what we've done so far in the search is we've looked at depth first search, breadth first search, lowest first, best first, and A star that all differ in how you select elements from the queue. Okay, so you can either a stack or a queue or a priority queue or, so how you select elements from the frontier, whether it's a stack, a queue, a priority queue, or what it's a priority queue on. And loop detection we did last time removes a path that loops back on itself. And multiple path pruning removes subsequent paths to a node. Does anyone have any questions about any of this? Okay. All right, let's do a clicker question. And I think I changed this so that it counts up. I think this is easy, so let's see if we can do it in 30 seconds, and if we can't. Okay. A star is admissible. What does this term mean? So what does it mean that A star is admissible? A, the first solution returned is the least cost solution. B, it always halts on finite graphs. C, it can get stuck in cycles. D, multiple path pruning is not used. Or E, multiple path pruning is used. Oh. All right, stick your hand up if you need more time. A couple of people need more time. You just came in. I'm not counting you. Anyone need more time still? Anyone need time? Okay, let's stop this. Yeah, the answer is A. The first solution returned . Oh, why doesn't that work? Why doesn't it let me click on it? Okay. So in fact, when we defined A star as admissible, when we did it, it actually didn't always halt on finite graphs. So the few people who did B were, okay. Any questions about that? Okay. One more. Which of the following assumptions was not made in the result that A star is admissible? A, arc costs are bounded above 0. B, branching factor is finite. C, h of n is an underestimate of the cost of the shortest path from n to a goal. Or D, the costs around the cycle must sum to 0. Okay, let's go. Anyone need more time? Need more time? No. All right, good. Yes, the answer is D. And in fact, the costs around a cycle can't sum to 0. No now graphs, right? Because then you need either all zeros or all negative things. Any questions about that? Okay. Good. All right. Today what we're going to do is we're going to start looking at how cycle checking and multiple path pruning, we're going to look at how they can prune this We're going to look at the complexity of them for the different search algorithms. We're going to use what's called the monotone restriction for A-star search. And then we're going to do something called iterative deepening and branch and bound that can save space so they're no longer exponential. Okay. So let's have a look at one of these just to make sure that everyone knows what's happening. So here is this graph that we did before. And if we just now do A-star search on this, what's going to happen with just A-star search is we're going to end up heading straight towards the goal. So it heads straight towards the goal. And then it's going to start wandering around and redoing things, and it's doing multiple paths because there's multiple solutions to it. And if I keep clicking here, it'll eventually fold in. It's awful. All right. I'm just got to select that one right in the top, then it'll work. You're supposed to notice that it's doing lots and lots of paths in there in the cycle, because this has lots of cycles in, right? And lots of multiple paths, and it should stop. There's any. I told you it stopped, so it's better. There's 100. Oh, my finger's hurting. Where's this going? Step. Oh, well, I'll put it on auto search. You can do the stepping for me. And it does it in. This is a different graph. Oh well, it'll eventually stop. I think this is because answering the question about what does this auto heuristic do. This is a really awful bad heuristic because it's the old heuristic, but I changed the path cost. Let's reset this. Reset it. Sorry. Let's do set node costs. Oh, cancel. Whoops. Node heuristics and edge costs automatically. Let's do this again. Solve this. Let's reset this search and do an auto solve. So if you change the automatic things, it messes it up, and it's going to solve it in. Because all these paths in here look good, right? All these paths in there going backwards and forwards look good because the path length hasn't increased that much. And I wonder if I can change this. All right. It did it with 162, right? 162 nodes expanded. What should happen if I turn on loop detection? If I reset this and I turn on loop detection, what will happen? Reset it. Should more or less or about the same, or a lot less? Okay, let's find this out. We'll do this a few times, and it's finding multiple paths, and it's 24. 24 with loop detection. Detection. And what happens if I turned on multiple path pruning instead? Reset this. What's going to happen? It's going to be the same, more or less than loop detection. It's going to be, let's try it. Right, it only has 15 with multiple path pruning. Okay. So it's good when you run these things to try and predict what's going to happen, and then try and see if your prediction is right, because that's how you're going to learn what's going on. Any questions about that? All right. Let's go back to here. Right, so how does multiple path pruning compare to cycle checking? Well, we know it's sometimes better. Is it ever worse? Can it ever be worse? Think about it. Can it ever be worse? Why not? No.
Because cycle checking will check to see if a node that's already visited in the same path has been, and then that will know that it's a cycle. But multiple path pruning checks if that node is in any path visited. So it includes the case that it's in the same path.
Right. Precisely. So if you have a cycle like this path is already visited. So multiple path pruning is also going to prune this path. So multiple path pruning always never does worse than loop detection. If a loop is detected, then multiple path pruning will detect it. Okay? So which search algorithms with multiple path pruning always halt on finite graphs? All of them, right? Because if they all halt with loop detection, then they all have to halt with multiple path pruning. So the answer here is all of them. So what's the time overhead of multiple path pruning? Oh. No, it's the overhead. We're already paying the number of nodes visited in time. Yeah. What's the number of nodes that were visited, remember? It's the number of nodes that were ever expanded. At each cost, you've got to remember an element of how fast can you check an element in a set? Let's assume you can do it in log n time by building a binary search tree or something else, right? So then, so the overhead is log of the number visited. This is the number of nodes visited. Well, number of nodes visited or expanded. Okay. So normally it's sort of linear. This is an overhead. We've got to multiply everything by log of v, because you keep checking for every time you're doing it. You're going to keep checking. Is it an element of the set I've already visited? Is it an element? Because that's the time we can check. We can add things and remove things from a set. Okay, so the log is the time to add and check for the elements of set. Okay. Any questions about that? That's something. Yeah.
What's the data structure of the set?
Binary search tree, hash table, I don't know, there's all sorts of things.
With a hash table, shouldn't it be constant?
Maybe, it's when it fills up. Or it can be this. Let's assume it's a. You can make it approximately constant, but then it fills. It's this funny. This one, I can guarantee, I can build it in log n time. Hash tables are weird because they depend on when you fill up, and then you have to redo things and rebuild them, and I can do this. What's a space complex, so space overhead? How much space do you need?
You only need that space for every node visited, so it's just B, right?
You need the space, yes, that's right. You need to store every node that's been visited. You need to store every node visited. Which in our case is just V. Okay. So is this better for depth first or breadth first searches? And why? Okay. To answer this question, let's go down to here. This is the table that we saw last time. So depth first search was initially, if you look at the top first there, was originally, wasn't admissible, it didn't halt, and it was linear. And things like A star and the other ones are exponential space. So what happens which is it better for? All right, question. Let's do this in code. For depth first search and loop detection, does it find the optimal path? Does it find a least cost path first if there is one? No. Does it always halt for finite graphs? Yes. And what's the space? In terms of path length? How much do you have to store? Right, remember we have a whole lot of paths. We might have a whole lot of paths. Right, in the worst case, it's sort of something like this. How much space does it require? Does depth first with loop detection require? With loop detection, what is it? How much space do you have? What do you have to search?
Linear?
Yeah, it's linear. You have to search up this path. So in terms of the path length, you have to search up this path. It's linear. Okay. What about for depth first search with multiple path pruning? Is it admissible? Does it find an optimal path? No. Does it halt? Yes. What's the space? Really? Why do you think that? With multiple path pruning, what do you have to remember? What do we have to store? Multiple path pruning, what do we have to store? Right, so if you're down here, what's the worst case? You have to store all of these things, everything you've ever seen. right? We have to store not just in this path length here, we have to store everything, right? We have to store this whole thing. How much is that then? It's exponential in the path length, right? So all of a sudden we've got to, for this one, for multiple path pruning and depth first search, it means we have to store everything. We have to store this whole tree, everything before it, everything expanded, everything breadth first search would do and possibly more. Right, we're down here, we have to store everything that, and it's exponential, yes.
Why is it not visible? Can you give example?
For,
It's not visible?
oh, because I might have the goal might be here, and you have to search, well, sorry, and there might be a goal here, 2 goals, and it flies down here and finds this one first before it finds this one, right? So it doesn't find the shortest goal. That's why it's not admissible. I mean, it's not even trying to find the shortest one. It's just trying the first one. What about A star with loop detection? Is it admissible? Does it halt? Oh. Sorry. Does it halt? And it has exponential space. What about A star with multiple path pruning? Is it admissible? Ooh. Is it admissible? No, okay. Answer is no, but put a star next to it because we'll get to that. All right. We'll talk about that in a second.